Welcome to day 34 of our STL course. Today we are diving into advanced practice problems designed to challenge and enhance your understanding of the standard template library. As you work through these real-world challenges, you will get the opportunity to apply your knowledge of STL containers, algorithms, and optimization techniques to solve complex problems. By the end of the day, you will feel more confident and ready to tackle any STL-based problem. Before we dive into the problems, let's quickly review the key learning objectives for today. By the end of this session, you will have learned how to solve complex problems using STL containers like vectors, maps, and DQs. You will also deepen your understanding of STL algorithms and how to use lambda functions and custom comparators to fine-tune your solutions. This day is all about practical application, so expect to walk away with the skills needed to tackle real-world problems efficiently. Now let's discuss an efficient problem-solving strategy for using STL. First, it's essential to understand the problem thoroughly. Identify the constraints and break the problem into smaller subproblems that can be tackled using STL containers and algorithms. Next, choose the right container, vectors for dynamic arrays, DQs for quick insertions or removals, or maps for key-value pairs, and of course use STL algorithms to streamline your code. Finally, always focus on optimizing your solution for both time and space complexity. By following this strategy, you will be able to approach any STL-based problem methodically and efficiently. Our first problem is sliding window maxima. Here we are given an array and a window size k, and our task is to find the maximum value within each sliding window of size k. This problem is often encountered in real-time monitoring systems, like tracking the highest stock price over a set period or monitoring CPU usage in a system. We can solve this problem efficiently by using a DQ to store the indices of arrays elements and ensure that the maximum element in the window is always accessible. The advantage of this approach is its n time complexity, which is far more efficient than brute forcing it with nested loops. Moving on to the frequency sort problems, where we are tasked with sorting a collection of elements based on their frequency of occurrence. The catch in case of a tie in frequency, we need to sort the elements themselves. This problem is common in tasks like ranking or categorizing data, where we need to identify and prioritize the most common items. We can use an unordered map to count the frequency of each element and a priority queue or max heap to sort elements by their frequency. Custom comparators allow us to handle the tie breaking by sorting elements alphabetically or numerically. This gives us an efficient and customizable solution. Problem 3 challenges us to find the top k most frequent words from a list. This is a natural extension of the previous problem, but with the added complexity of only returning the top k elements. Think of it as identifying top trending keywords from a body of text. Again, we will use an unordered map to count word occurrences and a priority queue to efficiently retrieve the k most frequent words. We will also use a custom comparator to handle situations where multiple words share the same frequency, ensuring they are sorted alphabetically. This problem is very useful in text analysis, search engines, or social media sentiment analysis. Next, let's tackle the group anagrams problem. We are given a list of strings and our task is to group all the anagrams together. The key to solving this problem is recognizing that anagrams, when sorted, will have identical character sequence. By sorting each string and using the sorted string as a key in an unordered map, we can easily group all anagrams together. This approach is commonly applied in tasks like spell checking or deduplicating text data. It's an efficient solution that can handle large datasets with minimal computational overhead. Problem 5 asks us to sort string T based on the custom order provided in string S. This problem requires a custom comparator where the sorting order of T is determined by the sequence of characters in S. A priority queue can help us achieve this ordering, and we will need to create a mapping of each character's position in S. This type of sorting is often useful in scenarios like localized sorting, where elements must be ordered based on specific linguistic or cultural rules. In our bonus problem, we need to schedule tasks while respecting a cooldown period between executions of the same task. This problem is common in task scheduling systems like CPU scheduling or event-driven applications where tasks must be spaced out to avoid overload. We can solve this problem using a priority queue to select the next task to execute and an unordered map to keep track of the remaining cooldown time for each task. This approach ensures we handle tasks in the optimal order while respecting the cooldown requirements. Now let's talk about some useful debugging and optimization tips. First, prefer using unordered map over map when you don't need the elements to be ordered, as it offers faster access times. Avoid unnecessary copying or sorting, especially when working with large datasets, as this can lead to performance bottlenecks. When working with large data, take advantage of STL algorithms like copy if and remove if to simplify your code and reduce the need for manual loops. Lastly, always profile your code with large inputs to catch any performance issues early and fine-tune your solutions. Now it's your turn to put your skills to the test. Choose one of these exciting hands-on challenges. Implement an LRU cache using unordered map and list. Create a music playlist manager using STL containers, or build a leaderboard using set or map with custom rules. These challenges will help you apply all the concepts you have learned today and reinforce your ability to use STL effectively in real-world scenarios. As we wrap up day 34, remember that solving advanced problems with STL is all about applying the right tools and algorithms in the right way. STL provides powerful containers and algorithms that make it possible to solve complex problems efficiently and elegantly. Keep experimenting with new problems, focusing on both performance and readability, and continue challenging yourself to master STL. You are now ready to take on even more advanced problems, whether in coding competitions, interviews, or real world projects.